Hello everybody! Today's topic is fuel cells and introduction. Terminator, The Rise of the Machines, Star Wars, Attack of the Clones, 007, A Quantum of Solace. What do they all have in common, apart from being very entertaining? Fuel cells make an appearance. Fuel cells power a hotel in the desert. Fuel cells power an aircraft. And fuel cells power the Terminator. So from a business case point of view, we see them in stationary and in mobile application. Going from science fiction to reality, in fact, fuel cells power office buildings from NASA, Google, eBay and more. Fuel cells powered the Apollo space mission, and fuel cells power vehicles. So we find them both in stationary and mobile applications. In the following minutes, I would like to present you the basic principles of a fuel cell. If you mix hydrogen and oxygen, give it a spark, a violent reaction will occur. Chemically seen, hydrogen reacts with oxygen to form water and release energy. The basic principle of a fuel cell is that you separate these two gases by a gas-tight membrane, the electrolyte. Then you divide the overall reaction in two parts, an oxidation and a reduction, which occur on both sides of the electrolyte on the electrodes. In this way, you convert the chemical energy in the fuel hydrogen directly into electrical energy and not via several steps, which gives you quite a high electrical efficiency. If you look at the main parts of a fuel cell, the electrolyte, cathode and anode, the oxidation reaction occurs on the anode. Ions are selectively transported through the electrolyte, and on the cathode side the reduction occurs. Here I have a specific example fueling a fuel cell, a low temperature fuel cell with hydrogen. On the anode side you oxidize hydrogen, you obtain protons and electrons. The protons travel through the electrolyte to the cathode, while the electrons go through an outer circuit because the electrolyte is an electrical insulator. On the cathode side, oxygen reacts with the protons under consumption of the electrons from the outer circuit, forming steam. The amount of electricity you can extract scales with the amount of fuel you provide and is thus only limited by the storage tank size, or where you will store the fuel, and not like in batteries where the energy you can extract is closely related to the amount of material you have in the battery. So here you can provide a larger scale electricity. There are a couple of major fuel cell types. They are divided according to the chemistry of the electrolyte, which determines the name, the type of elementary reactions and the operating conditions such as temperature and the type of fuel you can use. This table shows you the major types: alkaline fuel cells, polymer exchange membrane fuel cells, phosphoric acid fuel cells, solid oxide fuel cells, and molten carbonate fuel cells. And they are all according to the electrolyte chemistry named in this way. This electrolyte determines also which ion travels through the electrolyte. You see here OH-, protons, OH oxygen ions and carbonates. The transport mechanism through the electrolyte also determines the temperature where you operate the fuel cells. So here you can divide into low temperature and high temperature fuel cells, where the low temperature cells stop at around 200–220 degrees centigrade and the high temperature fuel cells start around 600 degrees centigrade. This also determines which fuels you can use. Low temperature fuel cells are typically fueled by hydrogen with different requirements on the purity of the gas, while the high temperature fuel cells, they can also use hydrocarbons. In the last line, the obtainable electrical efficiencies are listed. Apart from these major categories, there are also kind of subcategories developed from the single major types. For example, the direct methanol fuel cell and the high temperature PEM fuel cell. And they are all related to the normal, so to speak, polymer exchange membrane fuel cell. And they are tailored to the one to use methanol directly as a fuel and the other to operate at higher conditions where water is not liquid but vapor or steam. This was a basic introduction, and as a final demonstration I have two examples here: a high temperature fuel cell, a solid oxide fuel cell, and a low temperature fuel cell, a polymer exchange membrane fuel cell. Thank you very much.